Welcome to Essential Discrete Mathematics for Computer Science, Chapter 1, the Pigeonhole Principle. We begin our discussion of the Pigeonhole Principle with a very bold claim. In any group of 8 people, 2 people were born on the same day of the week. Now, we can try to test this claim in many different ways. For example, we're at a dinner party, and we have the guests Annie, Bob, Charlie, Donna, Eve, Freddie, Greg, and Hannah chatting, and we discover that Freddie and Greg were born on the same day of the week. While that anecdotal evidence gives us some proof of this claim, a skeptic might say, well, that's only one group of people. How can we convince you that this happens with any group of 8 people? Or would it happen with any group of 8 objects? The pigeonhole principle is a technique that we can use to show such claims. But before we get into these claims, let's build up some notation and basic concepts. The first concept is a set. A set is an unordered collection of distinct objects. For example, in the dinner party example, we had a set of people: Annie, Bob, Charlie, Donna, Eve, Freddie, Greg, and Hannah. We also have the days of the week: Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday. But we could have many other sets that we use. For example, just the numbers 1, 2, 3. We have the set Z, the set of integers. We have the set N, the set of natural numbers or non-negative integers. And we also have the set of real numbers. When we have a set, we're concerned about set membership. And we have the symbol that looks like an E to test set membership. This is an object X an element of a set A? Is X in A? So for example, with our set of people, we can ask, is Charlie in the set of people? Or we can use our set of days, and we can ask, is Sunday in our set of days? Whenever we have sets, we have the cardinality of a set. And the symbol for the cardinality of the set looks like 2 vertical lines next to the name of the set. The cardinality of the set is the number of distinct elements in the set. So if we have the set A, we have the symbol 2 vertical lines surrounding the A, and the cardinality of A is the number of distinct elements in the set A. The size, or the cardinality of a set, is a finite set is a non-negative integer. For example, when we have the set 12, 13, 14, and 15, the cardinality of that set is 4. When we have the set 1, 2, 3, the cardinality of that set is 3. For the set of people, Annie, Bob, Charlie, Donna, Eve, Fred, Greg, and Hannah, the cardinality of our set of people is 8. For the days of the week, we have Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday. The cardinality of that set is 7. Once we have sets, we can define functions or mapping between the sets. So we can have a function f going from a set X to a set Y. Each element of X will be associated with one element of the set Y. We call X the argument, and f of X equal to Y is the value of the function on the value X, its argument. F will map elements in X to an element in Y. In the dinner party example, we can map the dinner guests to the days of the week on which they were born. So for example, the guest Freddie will map to Friday. Freddie was born on a Friday. Now, with sets and functions, we've built up enough notation and concepts to introduce the pigeonhole principle. The pigeonhole principle is a very intuitive idea, so we'll speak of it that way and then introduce the formal notation. Intuitively, if there are n pigeons who are being placed into fewer than n pigeonholes, then some pigeonhole must have at least 2 pigeons. Let's formalize this concept now in terms of sets and functions. If we have a function between a set x and a set y, and the cardinality or the size of x is greater than the size of y, then there must exist 2 distinct elements in x, x1 and x2, that map to the same element in y. And for that, what we say is that f of x1 equals f of x2. Let's go back to our example of the dinner party. In any group of 8 people, 2 were born on the same day of the week. In this example, our set X is our group of guests at the dinner party. That's Annie, Bob, Charlie, Donna, Eve, Freddie, Greg, and Hannah. Our set Y are the days of the week: Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday. Our function mapping the people at the dinner party to the day on which they were born. So we can have Charlie mapping to Thursday if Charlie was born on Thursday, and Freddie mapping to Friday if Freddie was born on Friday. Now the pigeonhole principle tells us that since the cardinality of x, the number of people, is 8, is greater than the number of days of the week, 7, then at least 2 people must be mapped to the same day of the week, or 2 people must have been born on the same day of the week. We can generalize this principle, and this is called the extended pigeonhole principle. For any sets x and y, and any positive integer k, such that the cardinality of x is greater than k times the cardinality of y, if we have a mapping from x to y, and there are at least k plus 1 distinct elements in x that map to the same element in y. In particular, for k will use the ceiling function. So the ceiling function we're introducing, and the ceiling function takes an argument and it maps its argument to the smallest integer greater than it. So for example, when we had 8 dinner guests, that's the cardinality of x, and 7 days of the week, when we divide that, we have 1 and 1/7, but the ceiling function will round that up to the smallest integer greater than 1 and 1/7 to 2. So for this extended pigeonhole principle, the k will be the ceiling of the cardinality of x divided by the cardinality of y minus 1. So in the specific example that we just talked about with the dinner party, our k is equal to the cardinality of x, 8, divided by the cardinality of y, 7, minus 1. So for that, we'd have 2 minus 1. So if the cardinality of x is greater than y, then at least 2 distinct elements will map to the same element in y. And so as we can see, the extended pigeonhole principle generalizes the pigeonhole principle that we had just discussed.